I'd like to continue our discussion of Laplace's equation, and in particular we're going to look at a method of solving Laplace's equation using the separation of variables, and we're going to stay in the Cartesian coordinate system. So to begin with, let's look at a problem which is typical of the types of problems that we'll be solving using Laplace's equation. So what we have is really a 2D problem, although it looks 3D. What it consists of is this long channel that has these plates that are at zero potential, and they go to infinity in this direction, and they go to minus infinity to plus infinity along the z-axis. This end here has a plate that has different potentials depending on y. So as you go from 0 to a, which is the height of the plate, you could have any potential here that you would like as long as it's continuous and fairly well behaved. Here's another view of it. So here's our x-axis here, our top plate at 0, bottom plate at 0, and here's our v as a function of y. So this is x equals 0 in this position, so that gives us a function of y only, and that goes from 0 to a. The coordinate system that we're using is that this is the x-axis, here's the y-axis, and here's the z-axis. What are the boundary conditions? I've given them, but let's state them again. At y equals 0, v equals 0. So here's y equals 0, and so we're at this plate here, and so we have v equals 0. And that is true for all z, going from minus infinity to plus infinity. And it's true for x between 0 and x less than infinity. So what does that mean? It just means that this plate has those dimensions and it stays 0 everywhere where y is 0, and then we go up onto this plate and we're at y equals a. So here's what it says. At y equals a, v equals 0, z has the range minus infinity to plus infinity, and x goes from 0 to infinity. Now we have a little tougher boundary condition. This says that if we're between y equals 0 and y equals a, then the potential is equal to this function, which is a function of y only. So we're at x equals 0, and we're going up here in the y direction. This is the function that has to be satisfied here. This is a boundary condition. That's an important thing to remember. And here's the statement here, x equals 0. There's a reasonable deduction, which actually is pretty important, that we're going to make. And that is, as you go farther and farther away from this plate, you're in this channel. If there's any charge out here, you don't see it. And so what happens is the potential should go to 0. So at very large x, we should have v equals 0. V is the potential. It's independent of z. So we can always take any z we wish and call that z equals 0, and we'll get the same answer in this plane here as, say, a plane over here. Our equation will be a function of x and y only. So that's why this three-dimensional problem reduces to 2 dimensions, because of this geometry that we have here. So restating the boundary conditions, it's one thing to notice is that for 3 to be true, to be consistent with 1, so for this to be consistent with the first boundary condition, we need to emphasize that v of 0, the function v of 0 y, which is the function along that strip, has the property that at y equals 0, we have to have 0. And then at y equals a, this function has to be equal to 0. Why is that? Well, just go back here. It's because this plate and this plate are at 0 volts. So v of y has to go to 0 there. So what that means is that you can have a function. I've plotted it with the magnitude of the function in this direction. Here's the plate. That function has to be 0 here and here, but then it can be anything you wish here. And it can even have very, very steep rise in amplitude here. And actually, we'll look at that case. Let's write down Laplace's equation in 2 dimensions, just the second derivatives. And what we're going to assume, and this is really the big assumption here, is that we have separability. And that means we can write this function of x and y as a function of x only and a function of y only. If that's the case, then we can take our second derivatives of a product, these two products with respect to x and y, the second derivatives. For this derivative here, we don't have any x dependence here, so we can bring that outside. And so that's what we have here. We have y times that second derivative of capital X. And the same thing is true here. This does not depend on y, so we can bring it out. We have the function x of x times this second derivative here. And Laplace's equation, of course, says that these are equal to 0. So then we take this equation and divide by the product xy. Because you have already a y here, when you divide by xy, that will cancel. And so you're left with 1 over x of x, and then times that second derivative. And the same is true over here. You cancel the x function, and so you're left with 1 over y times the second derivative, and again it equals 0. We have this term here, which is a function of x only, and we have this term here, which is a function of y only. That may be a useful result because the sum of these two is equal to 0. So we're going to set each term equal to a constant, k squared and minus k squared, because they're independent. In other words, this only depends on y, this only depends on x. And so therefore, if we have these equal to constants, this one's say k squared, this one's minus k squared, we'll keep this equal to 0. There is one thing you might notice is k can be real or imaginary, so this should be a squared. If that's the case, then you redefine k in terms of the imaginary number k prime, and everything will work out, but it's just a little more difficult. We'll go with k and k squared real. Here's our term in terms of the second derivative of x in terms of plus k squared times x over x. Here we have minus k squared times y. The decision we made is to do that. That's an important decision and may be wrong. But you might have been better off putting k squared here and minus k squared here. It doesn't matter. You can do either one, but at some point you have to justify which one you want. The other thing to notice is that sometimes we write this as a full derivative, sometimes with a partial. In this case I use full derivatives because this term, this function here, or this equation, depends only on x. Over here it only depends on y, so I've used full derivatives. But we can go back and forth, and if there happened to have been a partial here, it wouldn't matter. Well, one thing we can do is just check to see if Laplace's equation still is satisfied. If you come up here and look at the second derivative of x with respect to x is equal to k squared of x. So if you take this equation and put in our solution, x times y, then it would look like this. So you'd have the first partial times this product, and then you take the second partial, and that gives you the second partial derivative. And the same goes for y. When you take that and finish the operation, you end up with this equation here where you have the second derivative of x with respect to x squared times y, and then the inverse y and x in these positions. Well, we can use the fact that this quantity here is k squared times capital X, and the other term is minus k squared times y, and so you'll have an xy equals 0. You can cancel those. You're left with k squared minus k squared is equal 0. So Laplace's equation is satisfied. So now we have these separated equations. Here's our x equation, and here's our y equation. And for the chosen signs, plus k squared minus k squared, we could solve those by hand, or let's just use Mathematica, so our only assumption is that k is real. So how do we do that? Well, we use the operator dsolve. This is for the x equation. So we put in the equation with a double equal sign. That's this equation right here. The primes just means take two derivatives. Here's the function we're trying to find, and here's the variable. The same goes for y, except now we have the minus sign corresponding to this minus sign. These are fancy printing outputs. It's going to print the x solution and the y solution for that choice of k and minus k squared. And that's these two results here. For a plus k squared for the x equation, we get e to the kx times a constant plus e to the minus kx times another constant. Now why do we get those two constants? Because we have no boundary conditions. We haven't used any boundary conditions. So a second derivative differential equation will give you two constants. Same goes for y, except with the minus sign we get the cosine sine behavior. Although these are C1, C2, these are really different from these. Just that Mathematica doesn't know what we're doing, so it gives them the same notation. So we'll change those eventually. Well, I turn this around. I put a minus sign for the x equation and a plus sign for the y equation. And all it does is just flips it back. So the x equation has the cosine dependence, but realize it's kx and not ky. And the same goes for y. It goes to the exponential form. And so that tells you then what happens when you switch these k-squareds. It just flips the type of solutions that you get. So let's relabel the constants just so we can stay sane. So we'll take the first version where we had a plus k squared for x minus k squared. And so realize that vxy can be various combinations of these products of x and y. And so let's just put the simplest case first. So we'll just name those constants a, b, and c, d. And I'll justify that choice where we want exponentials here in x, and we want sines and cosines over here. Here's the thing repeated. Here's our x equation, our y equation, and then or we could take the case where we switch the signs. What I want to show you are the real solutions, just like we found, and how it depends on the sign of k squared. What we found was that we had x in the exponential, and we had sines and cosines in the y dependence. The four terms could look like this. So you could have all of these terms, and that's basically what we had. Here's the exponentials. Here's the sines and cosines. But it's handy to put them in a table so you realize that the actual solution will be combinations of these solutions here. Okay, now if you switch, then the exponentials go over into the y dependence, and the sines and cosines go over to the sine and cosine, and so therefore you'd have combinations of these four types of terms. So linear combinations of 1 or 2 will give you the solution to Laplace's equation. There are some boundary conditions where you have combinations that yield cosh and sinh. Imagine up here if you had a e to the minus kx and an e to the kx without the cosine factors. You'd see here that the cos kx might have form like this, so you'd have e to the kx plus e to the minus kx over a constant, and that's cosh. And sinh is just the same thing with a minus sign here. If you have just the right boundary conditions, you may end up with a combination of the exponentials that looks like this, and you can use cosh and sinh. One other thing that kind of justifies what we did, if you have sines and cosines, then these oscillate. They don't go to very large numbers. They can be used to fit various functions, and we'll see how that is, but it's a Fourier fitting of a boundary condition by adding terms that have sines and cosines. The other thing it can do is help you eliminate terms by using symmetry. So the real solutions are all of the form like this. We're going to use this form here for our answer, and we'll take a look at the problem again. So I've repeated the boundary conditions. We want to see how to select the various types of solutions here that will fit our problem. Well, one thing is we expect the infinite channel in the x direction by this reasonable deduction to go to 0 for x going to infinity. This is not true for the sine and cosine, and it's certainly not true for e to the kx, k positive, but it is true for e to the minus kx. As a consequence, solutions with this factor are required because those will go to 0 in x as desired. The sines and cosines wouldn't do that. So that's why I said that this set of equations here, these set of terms, are important to have because of this dependence right here. We're going to throw out the e to the kx. The y dependence, involving both sine and cosine, can assure that we can fit the boundary condition 3. 1 and 2 will help us narrow things down. We're going to choose the version that I told you, k squared for the x minus k squared for the y. So going back, here's the whole thing again. We look at the functions, the full set of functions here. We have the exponentials here and the sine, cosine. We apply boundary condition 1, which is at y equals 0 in all values of x. The function vx of 0 equals 0. That has to do with the plate at x equals 0. It's grounded. So if you put in 0 for the value of y, so you're at y equals 0, then you have this function here times c sine of 0 plus d cosine 0 equals 0. Okay, so this is for any x, this would be a constant, but here we have a 0 right here and then a 1 right here. We're left with this quantity here, which in general is not equal to 0. We have sine of 0 equals 0, cosine of 0 equals 1, so we conclude that we have to let this be 0. The d has to be 0. We set d equal to 0 and it simplifies the equation to this form right here. Setting d equals 0 gives us this function that just repeats what we've already shown. So now we'll apply the second boundary condition, which said that at y equal a in all values of x, so vx0 is equal to 0. Y equal a. I should have put an a here, excuse me. And what that means is the top plate is grounded, so that's why we get this result. So substituting in y equals a into this equation, we get a sine ka and then the same factor out here. And this, because this is normally not 0, then you can see that we're going to have this function here equal to 0. We can't set c equal to 0 because that would throw away the whole solution. In other words, it would be 0 for all values of x. We don't want that. We conclude then that the sine of ka equals 0, and that has the property then that the product of ka is equal to n pi. Now we could take negative values, but we don't really need to because the positive values will give us the full solution. So we set k equal to n pi over a, just solving this for k. N here will be equal to 1, 2, and 3, and so on. We could have put in n equals 0, but that's a trivial solution for the original differential equation. We want to have non-trivial solutions, so we'll use n greater than 0. Okay, so now we're sitting here with the new sine function, and it's very useful to have this form. We'll now apply the condition number 4, which was the reasonable assumption, and that was that at x going to infinity, the potential goes to 0. So taking that expression here and letting it go to infinity, what we have then is this function here, where x is getting very, very large, and you can see that this term here goes to infinity, whereas this one goes to 0. We want the potential to go to 0, so therefore we throw away this term. We set a equal to 0. Okay, so because the Laplacian is a linear operator, and what that means is that if you have, say, functions f and g with constants a and b, you can take the Laplacian of the sum, and that will be the sum of the Laplacians. You could have 20 million terms here and it would still hold up. So if f and g are both solutions to Laplace's equation, then this sum, the af plus bg, is also a solution. Any linear combination of solutions is a solution, and this is a big deal. Redefining c sub n, which is now a new set of coefficients, the solution is sitting in this form right now. So we have a constant that depends on n, and we're summing from n equal 1 to infinity. And the reason we can do this is because of the linearity. So we can take any number of solutions and add them up. And all we're changing here is this integer n, which is in both terms. Right now, this is the solution, but we don't know these constants. So here's a repeat of that function. And one of the things we want to remember is e to the 0 is equal to 1. We can go back and apply our boundary conditions in a way that because we have this thing at 0x, x equals 0, equal to 1, if we're on that end plate, so at x equals 0, we're at a place where the function v can be looked at as an infinite series of this being a 1, c sub n times this quantity here. And that's what we stay here. So at v equals 0 y, so x equals 0, that's equal to our function v0 of y. This function here, we only have to define it between a and b, so that'll be a useful result. Okay, so how do we do that? Well, we multiply both sides by sine m pi y over a. But then we're going to integrate that product from 0 to a. This is known as the Fourier trick. What we're doing here is forming a Fourier series in the sine functions. Here's the integral. Here we have the integral from 0 to a, v0y of this sine function now is m dy. So let me just show you again how that came about. Here's v0y times this sum, and we multiply both sides by sine m pi over a y. Both sides. Okay, so here it is on the left hand side, and here it is on the right hand side. So it goes into the sum because we have the factor sine m pi a over y just times the whole summation here. Every term gets multiplied by this. Then we integrate over y, again from 0 to a. Taking the c sub n outside the integral, we have to know about this property here, that if you have the product of sines, the integral that you have here is equal to a divided by 2 times the canonical delta mn. Remember that that equals 1 if you have an equality of the two integers, and it's 0 if they're not equal. This is not too hard to prove. What it means is that if you take this integral, the only non-zero values will be where m is equal to n. So you can now identify this c sub n up here. C sub n will just be 2 over a, right here, times the integral of v0y sine of n pi y over a dy. So then you can put these c sub n's into our solution for v0y, and that's what this is here. And this is called the Fourier series of the function v0y. If you have an infinite number of terms, it will actually equal this function over here. Now, what we have is a function that is 0 at the endpoints. So at y equals 0 and y equals a, you get 0. That is a type of function where you only get the sine functions. Our boundary conditions took care of getting rid of cosine. I just want to emphasize that any function that starts at 0 and ends at 0 at y equal a can be represented by a sine Fourier series. So to repeat, the c sub n's are the Fourier coefficients. They generate a Fourier series in harmonic sine functions that represents this v0y. The harmonic idea is that you have n equal 1, 2, 3, 4, 5, and those are called harmonics because this is like a frequency. Here's our function. We're going to take a special one where it's just simply a constant for y greater than 0 less than a. And then it's 0 at the endpoints because that's the type of function we can fit with this Fourier series. So here we have the function. So we come up here from 0, we pop up to v0, we're constant at v0, and then we come back down to 0. And we're going to take this as a, and this is y equals 0. And the first thing we want to do is find the coefficients, and so therefore we can form the series. So right here we'll have this function put in. It's fairly simple because this function here between 0 and a is just v0. Going from the general equation for the sine coefficients, we can go specifically to these, and the n for the coefficient is right here. So you take out the constant v0, you take the integral of sine of n pi over a y dy 0 to a, and so here's the results. When you take that integral here, you get the constant right here, then you get minus a over n pi cosine n pi over a y, that's the integral, and then you evaluate that at the endpoints. If you do that, you could use this right here. You don't have to identify the fact that it's 0 if n is even, and it's equal to this if n is odd. Let me repeat. You don't have to do this. You could just use this as the coefficients. It will take care of itself, because as soon as you have n even, this becomes -1, and so you get 0. If n is odd, then this will be equal to +1, and so you'll get a 2. 2 times v0 over n pi is right here. So if n is odd, this is what it is. If it's even, you get 0. Again, just use this, or put in the fact that n is equal to an odd number, and so you would say 2m, this should be a minus sign, excuse me, this should be a minus sign. And here it is over here, 2m minus 1. C sub m is equal to 4v0 over 2m minus 1, which is only giving you the odd terms, which is equal to this quantity here. If m equal 1, which is odd, then this would be equal to 2 minus 1, and that will give you 4v0 over pi, which is non-zero, and so on. So just keep making this 1, 2, 3, 4, 5, and you'll get the coefficients, which we now will call C sub m, and those will take care of only the odd values of n. Let's repeat that. M is a new integer that we're going to use to convert n into an odd number. So if we do that, if m is going 1, 2, 3, 4, 5, this will always be odd, and so you'll get this particular value of the C sub m. Now we're going to stick back n, because n is favored by all physicists and mathematicians. That's why. So put it back in, and you'll have 4v0 over 2n minus 1, where we've gone in a circle and made this m equal to n. Now we can write the whole Fourier series, which is equal to this, and we can replace C sub n with the n-dependent coefficient. We have the full version of the Fourier series of this function in terms of the signs. One thing you should notice is this n down here will be such that as n increases, the coefficients get smaller. So we get a better and better representation as we increase n. We can't go to infinity, so we have to take some value of n max and put it here. The terms get smaller and smaller with higher n. And remember, this is the function that gave us this particular Fourier series. In practice, we go to n max, and increasing n max, we just keep increasing it until we are satisfied with a good representation of this function. So here's what it looks like. I've rewritten in Mathematica the exact same expression, and so this is exactly the same thing, where now instead of infinity we're going to go to n max. We take some particular values. This happens to be 100 for v0, and a equals 10. It's just a dimension that we just chose. Let's start with n equal 2, and then we'll go to 10, and then we'll go to 100, and then we go to 1,000. These are just plots of those results. So two terms give us this function here, which obviously is not a good fit. Then we go to 10. Well, it looks better. It's getting close to 100 up here. Then we go to 100. Other than these wiggles, it looks pretty good. And then finally we go to 1,000, and it looks pretty good here. I have to warn you, though, that there's still wiggles here. That effect is called the Gibbs effect, that you'll always, for these very, very rapidly changing functions, realize this thing goes 100, 0, bang, causing a lot of havoc in terms of the Fourier series. But you can see that if you can live with those wiggles, you've got a very good representation of that function. Let's go back and construct the series for the full potential. Now the full potential is a function of x and y. And this is valid for x between 0 and infinity, and for y between 0 and a. And remember, it's independent of z. So we have then the full solution, which I wrote in terms of c sub n's, and then I put in the c sub n. So this is the potential.